So what if we could change the rules a bit or a lot? That's the question I want to try to answer. And AI, I think, is a good solution. It's not the only solution, but in microscopy, we're often or always limited by these four, and there are other ways to plot this, but there's essentially these four kind of limitations that we have to circumvent to get the best possible image. And each system is better for one thing or better for the other, but you end up having to compromise between the four of them. What if we could change the rules somewhat in order to not compromise as much and get both low phototoxicity and very high temporal resolution? That would be really, really good, but it's very hard. So what if we could change that? And how would we change it? And that's something that we are very much engaged in, and we have a major NIH project ongoing currently called AIRS. That's AI platform for image restoration and virtual staining. That's the project that we're doing with Hari Sharoff and quite a lot of other people. There's, I think, 8 or 9 core facilities in the US that are helping us develop that platform. But I'll leave you with a question. So that's the question that we hope to be able to help with on the image quality side of things. So with that said, leave the question in the air and get going with the actual content. So we meaning humanoids, are around for 7 million years or so. And there was a new lineage was formed around 7 million years ago that broke away from that of chimpanzees. Similarly to those cousins of ours, the modern day chimpanzees, humans are very, very, very curious and highly innovative problem solvers. The rate at which we are creating smarter and more advanced tools and technology is increasing dramatically. And over the last 100 years, there's an enormous amount of new technology. So the rate of discovery and creation of technology seems to be much higher than ever. But before we go, just look at the last 100 years, if we quickly look at a little bit further back, 3 million years ago, we started to use stone tools. 1 million years ago, we mastered fire. About 5,000 years ago, we started to be able to write, and there's first evidence of writing. And 740 years ago, we invented the optical lenses, which kind of are the beginning of microscopy. The steam engine was 300 years ago, and machine learning is only 77. Could say only or already. But the concept of machine learning is from 1943, and so it's 77 years old. Now, there's an enormous amount of progress, especially in the last 5-10 years in this space. But if you think about it, it started nearly 80 years ago, and the rate of advancement that we see is dramatic. So can you imagine what it's going to be like in 10, 20, or 50 years from now? Not just about microscopy, but generally. I think there's a lot of interesting things that are likely to happen in the near future. So going back into the machine learning aspect of things, in 1943, Alan Turing was really the pioneer that started the whole conversation about machine learning, and he invented the Turing machine, which essentially is the precursor to the modern day computers. The key concept there was a single machine that can run multiple programs. And this was very, very exciting for the time, and it proves to be still a very good concept, and it's still used. He also mentioned the idea of potentially training the computers to do tasks on their own. But it was really Arthur Samuel, a little bit later than that, not much later, but contemporary, but a little bit later, that coined the term machine learning, and he illustrated the concept in action by teaching computers to learn to play checkers. and actually they managed to beat human experts at the time. So the concept of having data, having results, which we call ground truth, and then deriving rules was, which is basically supervised learning, is something that Arthur Samuel first illustrated and Alan Turing was conceptualizing. So a couple of steps forward, and I won't go into a lot of detail here because there is, we have a recorded webinar that goes into a lot of detail of the key developments and who did what. But I just wanted to mention 4 key names here. Jeff Hinton as the inventor or the researcher that popularized artificial neural networks and is currently at the University of Toronto and works also at Google. Yann LeCun, who is known for convolutional neural networks, and he basically built on the concept that that Jeff had, and he actually postdoced with Jeff Hinton. So it's not a big surprise that they are somehow related in terms of concepts as well. He's currently at NYU and at Facebook. In our space, there is Olaf Ronenberger. He's now at DeepMind Google, but he also has a position at Freiburg, and he's the inventor of the UNet, which is a specific type of convolutional neural network, and that has become extremely popular, primarily because it's relatively easy to train in comparison to other networks, and it's particularly good at doing segmentation jobs, so detection of objects. Because you can train it end to end and get not just prediction of what it could be, but also a segmentation map. And we use that as well. And the final name I want to mention here is Ian Goodfellow. And he invented the adversarial neural networks. And these are a very, very exciting, somewhat revolutionary way of doing deep learning by having 2 networks. One that is a generator, will generate potential, in this case, let's say images, and a discriminator that will do nothing else but to try and figure out, is the generator creating real images or looks real or doesn't look real. And so there is a little bit of an arms race between the generator and the discriminator in order to get ever more realistic image. So this is also has been expanded in the life science space in microscopy with a tool or type of network called CycleGAN that has been shown in a few publications in recent years. These technologies have initially been used primarily for fun, really. I mean, the potential was always great, but the examples that companies came up with were rather fun examples. I'd call them kind of marketing stunts. But that evolved, and in the last 5 years especially, it has become much more targeted and much more applicable to human life. So Microsoft, with conversational speech recognition, back in 2016 was already superior to humans. And in 2017, several examples, but one that I show here or talk about here is this one that allows for the prediction of heart attacks just from MRI, from MRI or CT. Can't remember right now, but I think there were MRIs. No, it must have been a CT. So they could already determine what, that's this company actually that managed to do this. So Arteris is from 2017, they were the first ones to get FDA approval for the diagnostics of heart disease. Viz.ai for stroke, and Imagen for bone disorders. So all of these are really applicable and having a positive impact on our life already. So generally, AI is definitely in the right track. There's concerns, of course. Lots of people have concerns about the potential negative use of AI for wars or for something else that isn't positive for humans. But generally, I think the use of this kind of technology is going to remain pretty restricted, and it's very, very narrow. Even the examples, the most advanced cases we have today are extremely narrow types of AI that are very good at a specific task, but not really good at interpreting complex environments, for example. One thing we could think of is one of the most advanced systems everybody knows about is the Tesla car. In there, there's maybe 15 to 20 deep learning models working together to figure out how to keep the car straight. But those models wouldn't be able to do anything out of that context. So they're very good at keeping the car going straight. They can identify road, they can identify people, other cars, but they are no good at identifying, for example, weather patterns. There are other models that are good for that. But there is no general, or we're not even close to a general artificial intelligence. We're very, very far away, in my opinion, perhaps centuries. Anyway, so the age of implementation is upon us. And this is a term that has been coined by Kai-Fu Lee in his really nice book, AI Superpowers. And essentially what that means is technology is there. In terms of deep learning, convolutional neural networks are extremely powerful. They can be used for a variety of things. And we're really just at the beginning. And this new beginning that is the last 10 years has been made possible primarily by these 4 key drivers. Very fast, cheap GPUs, a lot of annotated data, which we've not had we've never had this much, as well as open software and then platforms that allow you to use all of this together. So these 4 components have really made it possible to get to this accelerated rate of use of AI and rate of discovery of AI technology. So what about microscopy? There's a lot there too. We are lagging a little bit in comparison to other fields like fintech, so financial technology, or even healthcare. I think we're lagging behind that too. But I think that's normal because we're doing research. And so research tends to be a little bit more conservative and careful about what technology is used and needs to be validated properly. So I think it's right that we are going slower. So the rate of discovery is definitely impressive, though. Back in 2010 is the first paper that I can find using deep learning for image segmentation. And this is a paper from Turaga et al. From the Seung lab. Then in 2017, so this is a quick sequence of papers. 2017 from the Oskand lab, showing super resolution or increase in resolution using deep learning as well. Then Christiansen from the Allen Institute, accelerating or showing how to virtually paint data sets. This can be done both with GANs and with standard convolutional neural networks. We've done that with both, and it works very nicely as well. It's great for label-free imaging, like the systems that TomoCube or NanoLive have, or even more standard systems, just DIC phase contrast. You can train models to predict where the nuclei are. And we've done that going back 3 years now. Nearly 3 years ago, we launched Aivia 8 and Aivia Cloud, and that included a first model that predicted nuclei and a few other organelles. This is a very well-known paper, shows a modified UNet being used for denoising and also increase of Z resolution. That's the CARE paper. And this paper on the bottom here from the Alisman lab shows how to create the full pipeline from the training of the data all the way to applying using cloud computing. So these are, I would say, the 5 key papers in the last few years, that kind of landmark papers in the space of AI microscopy in terms of software. In terms of hardware, there's also some really interesting developments out there. And I'll just mention these three. So intelligent nanoscopy, this is for STED, so optimizing STED using machine learning. The one on the bottom is to optimize adaptive optics using machine learning as well. And perhaps one of my favorite papers of the last 5-10 years is this one with the autopilot, where it's a light sheet, pretty advanced light sheet system that reacts to the sample that it is imaging. This is very, very exciting, and that's definitely the future. And it reacts by doing analysis and then classification, and uses deep learning to figure out what kind of adjustments it needs to make in real time to the light sheet and to the imaging conditions to keep the best possible image acquired. So this is great because then you always have good data to analyze later on. So this all sounds amazing, but there is definitely an enormous gap, and there is a danger that that gap broadens if things continue as they are. So on the one hand, we have the biomedical scientists, where I would find myself, and I guess most of you on the meeting today are also on that side, microscopists, biologists, cell biologists, and so on. And then on the very other end are data scientists or physicists that have potentially little understanding about biology, but a lot of understanding about image analysis, machine learning, computer vision, and cloud computing. So we are trying at DR Vision and with Aivia, we're trying to bridge this gap as best as we can by creating tools that are easy to use and doing sessions like the one today that aims to kind of bring some greater understanding of how these things work and how you can use them yourself. So we use deep learning. Let me just check something because I think, oh no, it's correct. We use deep learning in a range of applications and machine learning in a range of applications as well. One of them is segmentation. So the general concept is shown here. So this is using supervised deep learning. We have ground truth created by hand or created by an automated recipe. The raw data, we can train a model that essentially learns a relationship between pixel to pixel or crop to crop between the raw data and the ground truth. And then given new raw data, it's possible to predict where the edges of the objects are, if that's what you trained it on. So one example, one of our early examples was with electron microscopy. We've now gone further, and we can do segmentation on other things, but with electron microscopy, which is typically very hard to do segmentation on, we have models pre-trained to go from this to a confidence map, which then we can use standard approaches to segment. We now have a project called ICA, so it's Intelligent Connectomics Analysis. That's the name of the project, together with Professor Rachel Wong and Dr. Wanqing at UW here in Washington, at Washington University. And the aim is really to reconstruct the neurons in the retina, in the visual cortex as well. So that's very exciting, and we're looking to study what kinds of circuits are formed, and also what kind of motifs of circuits we can identify, what kind of connections. And the first step is, of course, do the segmentation. And in this NIH project, we're doing the segmentation, the tracing, and then the circuit tracing as well. All of this powered by Aivia and Aivia Web. So this is the sequence of events that need to happen. So you get and we'll do this. We'll look at this data set together in the live demo in a moment. And this is a kind of segmentation that you can get from that. Definitely very powerful and relatively easy to use now that we've done a lot of troubleshooting to set up the whole infrastructure. We use a lot of the standard tools, and we've done a lot of customization as well to make sure that things work as easily as possible. Another application we have for deep learning is image restoration. This is a project that we started more than 2 years ago. Yeah, a little bit over 2 years ago, and relatively quickly we partnered with Hari Sharoff and Gigi Chen from the NIH, as well as a few others were added, but also with Hu Zhao from Texas A&M, and we now have examples, several examples. I'll show a few of them. So the concept is actually pretty similar. Instead of annotations, you provide, so the ground truth is not annotations, the ground truth is high quality data, or the target data, what I sometimes call target data, because that's what you want to get at the end. And the input data is low quality. Low quality essentially means you would love to be able to image without damaging the sample, for example, very, very fast. But if you do that with low laser light in order to keep the sample healthy, you get pretty rubbish image. So that's your input data, this rubbish image that doesn't hurt the sample, if talking about live sampling, live imaging. But we can then convert that to the target data, which typically is done with a fixed sample, so that we can get the very best possible image quality. But the concept is the same. So we have ground truth, you have an input data, you train a model that learns these relationships in a non-linear way, and that's the critical part. And then it is possible to take new input data and get this output data, which is it should be similar to the quality of the target data. It never is quite exactly the same. In many cases, it's not really necessary to be exactly the same. It's just needed to significantly improve from this input data in order to complete the experiment. So one example that we'll look at today is this one, and this data is from Hu Zhao at Texas A&M, as I mentioned. We initially trained the model with 10 pairs of images. 10 pairs of images, each image is 2K by 2K by 200 slices. And we had 10 images of high quality, 10 images of low quality, and then we trained the model. It takes about 3 hours using Aivia Cloud on GCP. Today, we're going to be using Aivia Cloud on a single GPU, so it's a little bit slower than that. It would be a lot slower than that. It'd probably be like 10 hours instead of 3. But that's what the data would look like. And you can see here, this is resonant scanning data. So there are lots of artifacts to do with that. There are line shifts. The data is almost binary if you look at close up. So there's a lot of artifacts. So we're not only improving the resolution, but also removing imaging artifacts in this case. This is one of the examples we will look at today together. If you look at the bigger field of view, that's the same example, but just a bigger field of view. This is what the ground truth data looks like, the raw data, and then the restored data. We are also going to do this exercise of doing structure similarity index. So this is one of the quality control parameters that we use. We have a few others, but we will illustrate this one today. And this essentially tries to identify differences between the ground truth and the raw, or the ground truth and the restored image. That's what this shows. And we'll be interpreting the results of these two kind of heat map pictures. In addition to the structure similarity index, which you can see improved a lot between the raw data and the restored data, we also looked at the normalized root mean square error, the signal to noise, and the peak signal to noise, and all of them go in the right direction. So here you can see the error going down, the signal to noise going up, and the peak signal to noise going quite a lot higher as well for this experiment. So in this example, the key was not, and I mentioned this before, but I think it's important to give some nuance here. The purpose of each experiment is very important. Sometimes the purpose is, as in this case, the purpose is speed up the imaging, the original imaging, and still get an image that is good enough quality to do quantitation on. The purpose was not get an image that is the same quality as the image I could get using a point scanner. So Hu Zhao was actually imaging with an SP8, a Leica SP8 resonance scanner, but doing lots of line averages and deconvolving, really beautiful images. But it was taking several days to image a whole mouse brain, so that's not practical. The computer would crash, the system would be unstable, the sample would dry up. I mean, all sorts of things. So his problem was it's taking too long, it's too error prone. So he needed to speed things up a lot. And the speed things up a lot meant he wanted to image with a single line scan on the resonance scanner, go as fast as possible, and still get good enough quality to do quantitation on it. And that's what we achieved with this result. In this particular experiment, that was the objective, was to get enough improvement to do image analysis on it. But in other cases, it's more about the sample sensitivity. And that's the next example. So next example is from the work we've done with Hari and Gigi. And here we have, this is done on the ISIM, which I'm sure you're familiar. So the structured, I just lost it. So it's an instant structured imaging microscopy. Jim, help me here. Instant structured illumination. That's the word, right? Structured illumination microscopy. So this system is pretty special because it doesn't require any computation to get the structured illumination microscopy done. It's done analogic, directly with the optics and with the hardware. The big advantage is you can do it a lot faster, and you don't need to take lots of images that you didn't need to process downstream in order to get a super resolved image or a high resolution image. So in this case, there are two channels, two labels, one for the mitochondria, one for the lysosomes, and you can see them separate here. So mitochondria and lysosomes separately. And this is the original data. And if we image at this laser light, which is very low, very reduced compared to the normal imaging conditions, this is very reduced, then we can keep the sample bright. And basically, it's alive, it's dividing, the cells are moving, everything is healthy, plus you keep all the fluorescence. If you image without deep learning, so the regular ISIM at the same amount of time points, basically the normalized intensity drops like a stone. Very, very quickly, you lose any ability to image the sample. Plus, you're probably damaging the sample too, because it's a lot more energy that you're depositing on that sample. So what does that look like? So that's the raw input data on the left and the restored data on the right. And we're not using UNet, we're using Arcan, and we can talk more about why that is. But it is impressive. I'm always amazed by how good of a restoration you can get, how good of an improvement you can get from this kind of data to this kind of data down here. And the sample stays very, very, very healthy, and it's possible to process it further down. So that's the same video we just saw. So the final example that I'll talk about in terms of restoration is confocal to STED. So here the aim is really to avoid using STED, which can be kind of tricky to set up and use, and instead just use a confocal, which a lot of people have access to in comparison to a STED microscope. So if you have a confocal and you can either train your model somewhere where you get a STED image, or you can go somewhere, train your model there with confocal and STED data, and then you have a model that you can just apply to confocal data and get high resolution image. So in this case, the aim or the test we wanted to do is, can we take a confocal image and make it higher, much higher resolution than just a confocal image, something similar to a STED image. And in fact, we got pretty close. You can see here the inset. We went from this kind of input to this kind of output, and the resolution is not as good as with the real STED, but it's very, very close. And some people actually prefer to look at this data than this data because it's less noisy as well. But definitely higher resolved, higher resolution. Okay, so I want to move on so that we can get to actually using Aivia as quickly as possible. But before we do that, I wanted to illustrate or just explain what we'll be using. So we'll be using this over here. That's Aivia Web, right on the top right of this chart. And Aivia Web is essentially the same kind of functionality that Aivia Desktop or local Aivia has. So you can visualize data, both raw and results. You can train and apply deep learning models, and you can do all of the video animation, basically everything that you can do on the desktop, you can also do on the Aivia Web. If you have heavy-duty jobs for deep learning, then we have also the Aivia Deep Learning Compute. And on this side, we're leveraging multi-GPU machines that are set up in GCP, so the Google Cloud platform. And that allows us to do things a lot faster and at scale. We can send jobs, initiate jobs from within Aivia Web or within Aivia. And today we won't be using this because it's really not necessary for this kind of hands-on session, but we'll be using the same interface to start jobs within Aivia Web. Okay, so wrapping up the presentation part, so we go to the actual hands-on session. So this is the Aivia team. You've seen this slide perhaps before. I think there's quite a few of us online today. So there's Quinn is definitely online in this session. Hoyen, Jim, and Trevor, I believe, are all here. But the team is even bigger than that. And we're currently looking to expand it with one more person based in Europe and one in the US. Our collaborators are amazing. And I want to thank them for their patience and their guidance and very interesting discussions with all of them. And we have active projects basically with everybody here currently. I mentioned before we have a large catalog of recorded lectures and tutorials on AI microscopy. The one that has, all of these are interesting, of course, but the later ones have more detail on deep learning. This one here also has quite a bit of detail on deep learning for microscopy. In some of them, I'm joined by others on the team, algorithm developers and data scientists. In others, I'm joined by Quinn or Hoyen or others that are also introducing different parts of the tools. In conclusion, I believe that deep learning is really, for microscopy, is really at its infancy. It's really only been a couple of years, a year or a couple of years since it became kind of mainstream. And DR Vision was there a long time before. So we've been using this kind of technology for 20 years. Machine learning and even deep learning. James has patents dating back, I think it's like 20 years, the first work that he has with deep learning. But it was not very productive at the time. But still, we've been active as a company, as a group since then. And now it becomes easy to use. So we're leveraging all of the expertise that we've gained over the years to try and create something that everybody can use. So definitely at the beginning, and it needs a lot of characterization. That's why we have these long-term projects with leading scientists like Hari Shroff and Gigi Chen and others to try and identify the limitations and mitigate those as best as possible. We are augmenting. I think the best way to do this is to augment existing pipelines. It doesn't really make a lot of sense to completely remove the current pipeline for image processing and replace it totally with a deep learning approach. It's unnecessary. It's much more efficient to find areas where there is a gap, there is a problem, and then try to address it with machine or deep learning when needed and when it makes sense. Very good. So we'll be using Aivia Web, as I mentioned. All of these applications are covered in Aivia Web. Actually, if you want to have your own version of Aivia for free, there's the Aivia community that allows you to view data as well as create annotations and see the preview of results. So it's a pretty good tool. It does the viewing job. You can create animations as well. And it does also some segmentation jobs using the pixel classifier that you can preview and save the annotations to collaboratively create more ground truth. And then you can train a model in a real full Aivia in order to apply it there. So you probably gathered we use AI in a variety of areas in Aivia. Object classification is something that we also do. I think Jim mentioned that in one of his webinars a few weeks ago. Today, I'm primarily going to be focusing on pixel classifier, the deep learning denoising. I will also show deep learning segmentation, and I won't go into the deep learning prediction today, but yeah, we could do that at any other time just to save us time today and to have enough time for the exercises. So brief introduction to Aivia. You may be familiar, but if you're not, this is what it looks like when you open it. At the very bottom, there is a panel that has a variety of things. One of them is the file gallery, but it will also show you measurements, spreadsheets. You can do some edits, and it's where you set up the video animations. The big window in the middle is where you can see the data, and that can be a 2D viewer or a 3D viewer or even a gallery. If you're keen on that, you can find it, or a planner view. And then the far right is a multi-purpose section. So there's this display settings for the volume and the surface objects. And then at the bottom is where all the analysis is actually done. These are adjustable. So to some extent, these can all be moved. And in fact, you can turn some of them on and off. But when you first started, this is what it looks like. When using Aivia Web, very important, you will get a link that Hoyen or Quinn will give you very, very soon, a link that is unique to you. This link will give you access to an instance that is running Aivia, and you can use it on your web browser. Please use only your link. Don't use somebody else's link, because you will be then looking at them using using the software and running the exercises. The Upstream toolbar is this cream kind of white color at the top, and this is not Aivia. This is additional functionality from the platform that we're using to run Aivia in, and it has a bunch of functionality, and we'll use some of that if needed. Sometimes there is some lag. We have servers in different locations in the world, so it shouldn't be too bad. But of course, these are remote computers that you're accessing, so there might be some lag sometimes. So give it a moment. But generally, we've had really good experience so far using these sessions. So these are the exercises we're going to be doing today. I'll start with the pixel classifier, then look at EM segmentation, and then we go to applying some pre-trained models, and then setting up a training job as well. So I think I'll pause here, let everybody get their own instances running, and I can also answer some questions if there's any questions. So, all right, any questions so far, or everybody's okay for now? No. So this is a pretty intimate session, which is great. We have plenty of time to talk with Alex and Matthias, and yeah, we do have those exercises to play with, but I think both of you will know quite a bit already about Aivia. You're both using Aivia, so it will be more kind of an advanced session, and I do welcome any specific questions that you have. This is a pretty good occasion to have a more kind of back and forth about what the workshop or what we're doing here. So let me get my Aivia Web ready or back in this screen. All right. Did you both get into your own Aivia Web?
Yes.
All right.
Yeah, for me, I just start to use this week.
Uh-huh.
Yeah, I had some issues to download the Aivia Web sessions, but now I'm downloading my file, which is big file, to the web. So I will see maybe the afternoon if the download is over.
Okay, so you're uploading or you're downloading after work.
Downloading.
Yeah, so you've already done some work and now you're downloading your results.
What did you say?
I was asking. You said that you were downloading Aivia Web. You mean the results of the what? I don't know. I guess I don't know what you're downloading.
No. I download my files on Aivia Web to use on Aivia Web.
Okay, so you're getting your files to Aivia Web.
Yeah.
Okay, I got it. Yeah. Okay, good.
Oh yeah.
So
maybe this week.
Okay, good. And how big is the file that you're preparing for Aivia Web?
Sorry, what did you say?
I was just asking how big is the file that you're going to use?
It's several gigabytes.
Okay, like 100 or 5?
No, 5, 6
Okay,
gigabytes.
okay. All right, and it's been uploading for a long time already?
This morning, and now it's only 10%.
Oh, really? Wow. So this is,
yeah,
I guess, pretty slow connection there.
Yeah, maybe it's the connection. I have to maybe link my computer to internet.
Is it a Wi-Fi connection?
Yeah, it's Wi-Fi connection.
Okay, so that might explain.
Yeah.
But still. Okay, so the first example I have, so you can get this data set from the download or I think it's called demo folder. So in File, just go to File and then Open, and you'll find the folder there for demo data sets. And then select it and go to the 3D 3D object analysis, and I think it's called 3D object analysis Drosophila, and then you will see, you can double click on this file. This is somehow up doing something. Okay, here we go. Now talking about download speeds, and I get this. This is not even
connected to the VPN.
No, I'm not. I'm not connected to the VPN, and I have a pretty good connection to the internet as well, which is, let's see, internet. Okay. Let's see. Run speed test. Peculiar. Should be okay. I'm just reconnecting, so I just refreshed that link. But it is not doing anything at all. It doesn't seem, it was, so one thing I'm going to check is my router, because it is possible that something happened that is not here, because it was working just fine a moment ago. Let me see. Turn this off. Just before I started, I obviously tried this and it was fine. and now it's kind of frozen. So I'll be right back.
Matthias, are you online?
Yeah.
Yeah, I think we're just waiting
Where are
for
you from?
Luciano.
Yeah, where are you from?
I'm from France.
Okay. Quel laboratoire?
Bonjour.
À Montpellier, IGF.
Comment ça va?
Oh, nice.
And
Très
you?
jaloux. Je suis à Houston, in the US, but I did all my study in Lyon, and I'm French as well.
Oh, okay. I come from Montpellier, and I'm now I do my postdoc in University of Washington in Seattle.
Oh, cool. Nice.
Okay.
Oh, Seattle, really nice.
Yeah, let's chat.
We should. Uh-oh. Not
Yeah.
looking good for Luciano.
No, it's not. It's not even. So nothing is working. So if any of my team members have their app stream open, they could try to do the first demo while I try to figure out what is going on here. I'm going to close my session and restart, which will be a couple of minutes. As you know, you've just done it. So I'm going to do that and see if it somehow gets better. I don't know why. Okay, so I have to wait a moment. Yeah, so
You gotta wait a few minutes. I'm on a different computer. Maybe Hoyen can try it.
so the first
Sorry,
demo.
give me a moment.
Yeah, the first
Okay.
demo point is just the Drosophila data set with the pixel classifier, and I was going to use the 3D magic wand to train in a small region and then apply on a bigger region and show the magic wand in 3D. That was the main thing, and then edit a little bit the training data in 2D. But I wanted to show the 3D first and then the 2D after.
Yeah, actually, I just started this session as well. I think you are like about 15% ahead of me.
Okay, so hopefully it will just resolve itself by doing this, but I have not seen that before. It was just fine before.
I think like it's a very rare occasion that happens. So like typically just logging off and just logging back in have always been working for me. So just to like it's kind of like one of those things like where you just like kind of like turn it off and on again, and then it will just suddenly work.
Yes, hopefully. Well, if it doesn't,
Interesting.
to figure it out.
There might be an issue, Luciano, because I realized I'm on a different computer, but it's Aivia Web. I don't need to be where Aivia is, and I can't log in. I'm getting an error message that says no streaming resources are available for your session. So maybe I'll ping Sean real fast and just make sure that everything's up and running.
Yeah, go ahead. But we can get going. So for Alex,
yours is working. Okay.
Yeah. So you go into demo data, and then the data set is called 3D Object Analysis Demo. Press that, go open, and that will open this nice data set that you saw. That you probably saw in some of the demos before. It will open in 2D, but you're familiar with the views. So the views are at the top there. Yep. You can go to 3D, and then you have the 3D view. And what I'm going to be using is the pixel classifier. So that's the first kind of machine learning tool that I want to explore a little bit with you. I really like the 3D magic wand. That's why I'm going to play around with it, because it's one of my favorite ways to train, because I'm lazy and I like to do things quickly. So I'm adjusting the lookup table. I assume you know how to do this, but if you don't, you can check what I'm doing. It is important to do that because the magic wand is going to interact with what is visible, not the, let's say, raw data, but what you decide you want to choose. So if I set the view like this, it will interact with the voxels that are visible right now. And if I set the view like that, it will interact with these voxels that are visible now. So it is dynamic, and we made that, it's by design. So in the pixel classifier view, I'm going to set the region of interest, and I'm going to say that I want to apply also in the region of interest, and I'm going to use a clip mode, which gets rid of nearly all of the data and just shows this small piece. Then I'm going to adjust it so I get a small chunk of it visible at the top, like this. And the magic wand is by default on, so I'll leave it on. But if it's off, it will look like that, so it has no highlight. If it's on, it's like this. And I'm going to click on it. So you can see it painted a pretty big region, or it previewed the painting of a big region. I actually want to paint a pretty small region, and I'm going to adjust. This is also dependent on where you click. So if you click closer to the center, it gets a smaller area. Closer to the edge, it will apply a different threshold, and it will be a bigger closer to the edge of the object. So that's my teaching region. And by doing this, if I do paint, this will now take the input from this whole box, the box that you see here, this yellow box. Everything that is highlighted in gray is going to be input as the wand class, so the foreground. And everything that is in the box but outside of the gray preview is going to be taken in as background. So we will not use it for the wand. So I switch here to segmentation because that's the segment. I want segmentation, not a confidence map. And I can just now preview. So the preview runs within the ROI that I specified. So we'll pretty quickly see meshes in here, or surfaces. And it's still calculating those. Yeah, they're there. So this is a preview of this region. It is pretty close to what I wanted to achieve. So there's not a lot more painting that I will want to do. So I can just teach at this point. So I use the magic wand, I hit paint to take those voxels in either as one channel or background. Then I taught it, so now it's kind of saved in a trained classifier, which I can export using the export functions of the classifier, and I can apply it on other images, or I can further enhance it with additional annotations from other images. Yeah.
Do you mind going through the different options in saving?
Yeah,
because
sure.
This is always a nightmare. I always save all four because I never know which one is actually going to contain both the data and the recipe.
Well, this is the best one. Copy everything. So this,
okay.
So if you use the bottom one, it's kind of like from least amount of stuff saved all the way to the most amount of stuff saved. That's what it is. So save classifier.
So what would be,
yeah.
Sorry. So what would be the point of saving just the classifier if the training set doesn't follow? That's the reason. That's the thing that confused me a little bit.
So you may want to save the trained classifier in the case that you just want to apply it to other images. You don't want to change it ever again. So you just want the classifier. You want the classifier, you want to apply it to a bunch of things, and you want to send the classifier to somebody else. Let's say, I mean, we work with CROs, and they create classifiers and then give it to their customers. And they don't, the customers don't have a way to train anything. So they just have the classifier and they can apply it to a bunch of images. That's it. If you do save the training set, that will also have oh, I get confused too. So the training set, I think it also has the annotations. But then the next one is the confusing one. Annotations for the current image alone. So what's the, maybe
the training set is the default common one. That's the one that I swap back and forth with people. It includes the annotations, and you can still edit the classifier.
Right, but the classifier doesn't have annotations. I know that. And what about this one here? So save annotations for the current image. So that's just the annotations, nothing else, no classifier, and nothing from other images, just from this image. And the bottom one will have all the data and the training data, which means all the annotations for all the images that you've trained with, and that will take the whole thing. So that can make, depending on which images you used, it can make a pretty large folder, because it will try to copy everything, right? It will try to copy all the images that you used for training plus all the annotations into one spot.
Okay, I see. If you save the annotation, can you reload them afterwards and change them?
Yeah, you can.
Okay.
They're saved. You need to, of course, you need to open the image from which they came from together in order to make any meaningful change, right?
Yeah, sure.
But
okay.
that's why we have this option to save the image and the annotation in case, people, some people are not so good at keeping track of what they used. So this way it keeps the whole thing together. But if you're good at keeping track of what you've done, the training set is the safe one, because it will keep all the annotations for whatever you train. So if you've used, you have a folder with 10 images and you've opened each one and created some annotations for each one of the training images, then you save the classifier or save the training set. In this case, save the training set. It will save all these annotations. And so you can revisit. Yeah.
Thank you.
Yeah, no problem. And it helps me also think about it since we did it. I don't think I thought about it since. So good reminder for me too. Okay, so I already taught it, so I can now apply it, and I'm going to apply it to this region, and we'll get meshes. So actually applying the classifier just as a confidence map is very fast. So if I do that, we'll get the new channel. So I'll just apply here, and it's actually nearly instantaneous. So that's the time it takes to apply the classifier to create kind of enhanced channel based on what we trained. What takes a little while is to create the meshes, which I did as well. So now we have the meshes here for those objects. The next thing I wanted to show is classifying these meshes as with the object classifier. I don't know if any of you has used it yet.
Yes.
You have? Okay. Was this Alex?
Yes. Sorry.
Okay. So the object classifier lives over here for Matthias if he hasn't tried it yet. So the object classifier is really good if you're trying to create or study different phenotypes of cells. Or if you don't really know what phenotypes you might have, it also has something called novelty detection, which will give you a score for how likely a cell is of being part of a class you have not trained for. So this is what it looks like, how you use it. In this case, it's a classifier. You have multiple options depending on what you've created. This case is just a mesh, so we can classify any number of things. You can see everything that is listed here, but right now we have meshes only, so I'm going to do that. And on the right-hand side, it will show me a thumbnail of all the 3D meshes that we generated in this image. And then you can create as many classes as you want. So I'll call this phenotype 1, phenotype 1, and this will be phenotype 2. And red and green are not great for me, so I'm going to change it to some other color like blue. Right. So I now have these two classes. They have nothing in them, and you can select cells based on. You can select them directly from the view. That's perhaps one of the easiest ways to do it, is to select them from here. Let me turn off the ROI so that I can more easily interact with this. Okay. So you can interact with it here, and I'm using the control and then click, control click. So I'm selecting a few cells, select them from here, or I can select them from here, or I can select them even from a spreadsheet. I'm going to assign them. So I assign them to class 1. And now I pick my class 2 or
Wait, I didn't see that. How did you select it from the spreadsheet?
Oh, from the, it's just, you just click on it. A spreadsheet with control shift, control,
Oh, okay,
and then
right.
control click is the way. Now I'm going to select some of these smaller ones now. Or you can do, I'd actually, the way I did it just a moment ago was actually directly in the 3D view, not in the spreadsheet. I did click on the 3D view, and it works just the same. But because this whole thing is connected up, it actually shows the selection also on the spreadsheet. Then I assigned it to this other class. So now I have a few counts, so a few cells in this class, a few cells in this class. I have not taught anything yet, and so it's not ready to apply. But teaching is pretty straightforward. So you hit teach down here, and it will take all the measurements that are available for these meshes and create a classifier similar to the pixel classifier in terms of technology, but now it looks at measurements, not really the voxel or pixel information directly. And then I can apply it. When I apply it, it's going to take all the objects and classify them as class phenotype 2 or phenotype 1. And I also turn on this detect novelties, which is going to give me a score for how likely a particular cell is of being of a different class, other than the 2 that I trained on. That's done. I have 25 cells that are in one class and 42 in the other class. I can turn off this viewer mode, and I'm going to use the color coding of Aivia to color by class. Oh, it was just there. Color by class, and let me see which cells are of one phenotype versus the other phenotype. Yeah.
Okay, sorry. Do you influence the pixel classifier choices by having more or less column present in your spreadsheet?
Influence, say again?
Sorry, the connection is now really bad. In your spreadsheet, you can add or remove measurements, right?
Yes.
Does this change how the pixel classifier would, not the pixel classifier, the object classifier would behave for the classification?
Because you can choose which measurements are going to be considered for the object classification. So it does make a big difference. Yeah, it does.
Okay. Okay. So you have to show the measurements that you want the object classifier to use to discriminate your object. Okay. Okay. Got it.
Or we will just use whatever is. So if you don't choose, we will choose for you a subset of the measurements. But if you streamline it and have a group that you're interested in, then you can choose it as well. So let me see. I'm getting a message here, I guess, from somebody on the team. Oh, the audio is breaking. Sorry, Alex.
That's all right. You're back. You're back. I heard the last 20 seconds.
Okay. All right. So I have classified, and I have the subtabs down here with the classes, and it's even possible to see in the spreadsheet as well. So I can classify by group. Can set this to 0 and this to 3 so that you can see the groups. So they are visible here. So this is one group, this is the other group, and you can also see how confident we are per group. So it's 100% confidence. So it's 100% confidence that it's true, and we have any? Yeah, we do have others that are not 100%. Yeah, one. to try and take over, because I don't know if I'll be able to better this.
Okay, just give me a quick moment to get to where you are on the image, and then and then I can take over.
And then we'll be setting up a model, training ourselves.
Yep. Sorry, I just had the wrong file open. So, okay, so just quickly. Okay. Yeah, mine was frozen for a little bit too. Okay. So.
Okay, I stopped sharing mine because I don't think I'll be able to do much more. Apologies for that. Not a lot I can do from here. I think it's going to be much smoother running from Hoyen's computer or Hoyen's location, because it's nothing major is happening, I think, in Seattle right now.
Yeah, no problem. So let me go ahead and just share my screen, and then let's. Okay. So right now I'm just training the pixel classifier so that we can get to the where you guys were on the slides. So previously, I think we were already at the pixel. We're at the object classifier, correct?
Yeah, I mean, I don't even know if it's necessary to redo all of this.
Okay.
We had already done it. So the pixel classifier, I think it's more, next thing was just asking if they were able to do it.
Yeah, maybe we can move on to the next image.
Where I was.
Next exercise.
Yeah.
Yeah.
Okay.
Yeah.
All right. So what's next? And I have
EM set.
Okay, EM data set. Sounds good. Okay. So let me
that's
just go ahead.
specialty.
So we're going to open up the EM data set. If you go to a file open and go to the shared data folder, we have the EM analysis demo image. Can just open that. Okay. So you guys, are you guys okay with this part already?
Yes.
Okay. So with the EM analysis, we have already pre-trained a model that.
Wait, I don't.
Sorry.
I replied, but I'm not met yet.
Oh, sorry. Yeah, my bad. Okay.
Yes, I'm okay too.
Okay. 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 You guys both have the image?
Yes.
Okay, great. All right. Yeah. So we have pre-trained a model for the EM data for EM analysis using UNet to do the segmentation. So in the recipe console, you can go to the recipe drop-down list and select the 3D EM analysis recipe. With the way that the EM analysis recipe works is that it is going to transform this image from this kind of grayscale EM style data to something that is more fluorescent-like. So we'll have very black edges around all of the cell borders, and then it will be very bright in the middle. So we'll start. Let me go to the. So for this one, I think. Really just in terms of the parameter settings, it's I kind of have a lot of this have been set up so that it's it should work by default on this demo data set, but we can just click on the look at the preview by clicking on this preview button here. And this should be generating a probability map, or at least an outline of the segmentation that you're going to be able to adjust. And there's a few parameters here. So there's the intensity threshold, which is going to be based on the segmentation, which is segmenting the probability map output image in terms. And then the next option, so this is one, is the use 2D or 3D kernel. So depending on the type of parameters depending on the type of analysis that you're doing, you can, if you use the 2D kernels, this will apply the unit based on just the 2D, just on the 2D image. So it'll take specific sections of the image on 2D. Whereas for 3D, it will take into account, in addition to each slice, you will also take into account of the 3D, the slice above and below that as well. So have the preview generated, and you can click on this detection channel preview, you can see what the result preview looks like. The cell region is highlighted in blue. You can turn this off so you can see where I can the intensity settings. Okay. And then you can, if you look at the very bottom of the image, so right below where the 3D object analysis, you can see there is a little, there's a very small section that says things like X, Y, and intensity. So sorry, my screen is a little bit, it's pretty high res. So like so everything it's probably looking really small for you guys. But if you look at just look at the very bottom, you will also find that on your image as well. So you can kind of mouse over the image and see what the intensity is, and then adjust your intensity threshold parameter based on the number that you see.
Yeah, I can see everything very well, Hoyen. Even though your screen is high res, it looks good.
Okay, great. Do you guys have any questions about this part?
No, all good.
Okay, great. And then for the next part, and for the subset filtering, this one is going to be a little bit trickier, because what the parameter is going to be is based on is the size of the object in 3 dimensions. So the volume itself can be a little bit tricky to calculate. So I would just start off with something like either small or medium, and just to see where if you get the detection result. If you don't, then try to decrease it a little bit further. But also, but if you're starting to see like a lot of just smaller, like really small objects that you don't want, you can change the object size to a higher value. And then the smoothing factor allows you to change how the smoothness of the mesh output. If you set this to 0, then the output mesh will look like it has like a bunch of steps. So I don't know if you guys like played Minecraft or like have seen what Minecraft looks like. Like, yeah, basically that's what you're going to be looking at if you're looking at when you set the smoothing factor to 0.
Yes.
I'm also going to increase the intensity threshold because I think this is a little bit over segmented.
Mm.
And so it takes a little bit of time to generate the preview. And of course, it depends on how big your data set is. In this case, I have a pretty small image. It's 512 by 512 by 10. So it's not so bad. But if you're looking at a full-size EM data set, maybe like you need to like try to consider using the region of interest to generate the preview. Like once I'm happy with the result, I can just go ahead and just click start, and then this will apply the deep learning model, and it will generate the probability map and then do the segmentation of the object. Do you guys have any questions?
Not at this stage, no. Thank you.
Okay.
Can you see it in 3D? The meshes, I mean?
The preview does not support the meshes, if I remember correctly.
Yeah, you're right. I'm just asking about the 3D once it's processed.
It should.
Yeah.
Hopefully.
This wasn't a trick question for you, Juan. It was a question for the guys, for Alex and Matthias.
Oh, it's still pre-processing image.
Okay. Very good. One thing I have not done yet is to try and do an apply on an ROI with this recipe. I don't think I've done that because the ROI, this kind of ROI with the clipping and so on, this is something relatively new that post-dates the launch of this particular recipe. So I don't think I have tried this particular recipe, and that would be pretty useful actually for large data sets when you have really lots of maybe 30,000 pixels by 30,000 pixels by, I don't know, 5,000. If you have a big EM block that you've imaged, you might want to apply it on smaller chunk rather than on the whole thing.
Yeah, I mean, even after applying, you can see that I actually have the parameters set incorrectly, so I'm actually not seeing any mesh at all.
You're not getting any? Okay.
Yeah, I might actually need to dial it down by quite a bit. So just say 2,000.
Object size, I think it's a lot less. And you could also try the ROI apply so that you don't have to wait so long.
Good idea, actually. Yeah.
So whoever gets meshes before Hoyen gets ice cream on me.
Damn.
You might have to go to Portugal to get it.
or a beer, whichever one you prefer.
I wouldn't mind going to Portugal for ice cream right now.
They're both French. How about a glass of wine?
Also that. But I don't know how.
Yeah, but not an American one, please.
Exactly. I was going to say, that's going to be expensive. If finding good French wine in the US is going to cost me a lot. Yeah. Okay, Hoyen did it. Okay.
Yep.
Safe.
All right.
Unless somebody did it before.
Yeah. So I'll can I get a glass of Vinho Verde then?
You can. Yes. I can even buy it. I can buy it in QFC. They have Vinho Verde there.
It's true, yeah. So I've actually since it's been kind of hot the last few days in Seattle, so it's been very nice to have just a glass of Vinho Verde with dinner. So, and plus I had a seafood paella that I made, so it was a very good pairing.
Cool. So you got the right parameters. What did you use so that the Alex and Matthias can also try it?
I used 2,000.
Okay, 2001. All right. Yeah.
And your intensity threshold is 120. Okay.
And 120 at the top, yeah.
At the threshold,
you can try to pause the processing. There is a pause button there, which will unlock the GUI and at the earliest convenience. So it doesn't immediately pause. It will pause once it gets to a natural spot in the algorithm that it's running. So it might still take a couple of moments to show it to you, but then you can run it. So while this is happening, I don't know, Hoyen, do you want to continue?
Mm-hmm. Yeah. So I'll just wait and so I think this pretty much covers the portion of just doing the EM analysis using the recipe. But let's say, for example, if I wanted to say train a new data set, then we can actually do the ground truth generation right here in Aivia.
Yeah.
But for some reason, I think right now my GPU is not responding to my results either. So I need to, let me see if I can reload this data set and then, or just open a new copy of this.
In the meantime, my Aivia Web is now running nicely. Let me check my speed again. Maybe half of the people already. Yeah, now it's back to 30 megabits per second. It was like 2 megabits per second a moment ago.
Yeah. Okay. So I'm just going to wait for a little bit. So you guys are you guys okay with the, is it still processing right now?
I have my result.
Okay,
For me, it's still running, but I don't have the same images. I have the same image, but the analysis is not the same. I don't know why.
The result is not the same.
Yeah, the result is I did the analysis one, and it was not working, and now I do it again.
Okay.
And I obtained something really rare.
Yeah, can I jump into your session and see what it looks like?
Yeah, sure.
Let me see, which one is that?
Should be Matthias.
Yeah, but let's see which one that is on the list here. So Matthias is there. What does it look like right now? Are you rotating your screen or not? Is it flat?
Yeah, I can rotate it.
If you turn off your raw channel, the input channel, then the segmentation really jumps out at you. Sometimes because especially EM images are so bright white that it overshadows the segmentation. So if you go to channel settings and turn off your inputs.
So I'm rotating your image now, I think.
Oh yeah, that's working. Okay.
Yeah. See how that color just jumps out at you now?
Yeah. It off. So Matthias, let me show you. Let me see if something here works. It does look like it's kind of merging too much, right? So the thresholding probably should be a little higher than what you have used, because I see a lot of the neurons are kind of merged together there. Yeah, there you see it as well, right?
Alter here, this green.
Yeah.
Yeah. Very good. And also, yeah.
Let me show you something else too. You can add like an ortho slicer. That adds a pretty cool effect.
Mm-hmm.
Okay.
Because then you can kind of see the outlines.
Okay, yeah, Hoyen, go ahead. I realize that I'm just looking at the time now, and I realize we're kind of already 2 minutes beyond the time.
All right. Yeah. Okay, sounds good. Okay, so for example, if I want, continuing on, so this EM analysis recipe is trained to detect cell bodies. But let's say, for example, if you wanted to detect something that are different from what we have trained a model for. So, and you need to generate new data sets. So say, for example, I'm looking to train on the mitochondria. I can do that using I can create the ground truth using the 3D tools. So we go back to the 3D view. Going to turn off the ortho slicer. And then when we go to on the right, when you look at the analysis tools, there's the 3D tools tab. You click on that, and the second icon called the mesh contour editor. When you open that, this kind of changes your whole screen. So I'm actually going to turn that off just because it's a little bit easier for me to actually look at this, kind of like in this way. So when you can actually create a new slice by clicking on Start New, and when you do that, then you can start using. Then you can kind of mouse over the image somewhere. See, so this is a little bit small. Let me zoom in a little bit. So I want to probably need to change my orientation a little bit. So I'm going to. Oh, wait. Is that? Oh, I'm going to turn off the enable painting. Okay. And you can also change the thickness of the orthoplane if it becomes too dim, so that you can actually it makes it a little bit easier to kind of look at what you're looking at. And then once I'm ready, I can go back to enable painting. Okay, I guess this doesn't actually do that. All right. Anyways, so you can
when
So
you're
what's that?
yeah, I was saying on the when you're on the mesh editor, it always shows a single slice to make sure that you can see it. If you want to make it brighter, just use the lookup table to make it brighter and keep it 100% orthogonal to the view. If you put it at the tilt at an angle, it will not look good. Yeah, so like this, now adjust. Well, that looks weird. Check the bottom left. I think the bottom left sphere is probably not actually at the bottom. You know, the
I'm actually in the middle slice right now.
no, I mean on the lookup table there are 3 little dots, spheres that control on the lookup table that control the opacity. The one you created is fine, but the further one on the left, I don't know if it's actually at the 0 at the bottom.
Yeah, I don't know either.
But can you pick it up and drop it back to the bottom just to make sure that it is there? Because I think the lookup table looks, or the display looks a bit odd.
Yeah, you just go back to the original. So I'm going to reset my view right now.
Yeah.
And then, so I think, well, so actually another thing too is that since I'm actually on composite view, you change it to max projection, it might actually help.
That's what it is, yes. Yeah, okay, good that we got it.
Yeah, okay, so I'm going to go back to enable painting. So there's a couple of tools. There's the paintbrush, there's the erase, flood fill. You can also delete or copy a region. And then if you open up the advanced, there's also additional options that you can do. So for now, I'm just going to keep all of these options on. So what this does is whenever I draw on the region, after I finish drawing this up, this will automatically enclose, when I release my mouse click, it will automatically enclose and fill the area that I have enclosed there, and then move on to the next step. And then on the next step, since I also have the auto draw option on, so this one will try to predict what the shape of the object looks like in the next slice. And you can, if it doesn't look right, you can fix that by going to the erase or using the paintbrush to add or subtract regions. And same idea, you just use your left mouse click right on the image to do that. And then when this is done, you can step to the next step. Am I going too fast? Sorry.
No, it's okay.
Okay. All right, so as I step down or step up, like you'll notice that like it will generate the prediction on each slice. And so like for now, I think like most of it looks pretty good. So I'm just going to kind of just call it, except for this one. So when I'm ready to finalize this object, I can just go ahead and click complete mesh, and this will create a new object set. If I want to smooth the object out a little bit, I can turn this option on. For now, I'm just going to just do the complete mesh on this one. And just to give you guys a view of what it actually looks like, I'm going to, in the 3D display options on the ortho plane, I will turn off the mesh slice so you can see how my, kind of see how my slice look on the slice, on the result image here. And then I'm going to do another one. This. It doesn't seem to be. Okay. Okay. So it was just kind of being slow. So again, I think it's pretty important to actually like make sure you keep like have the view so that it's orthogonal to what you're looking at, so that you can actually see what's going on. Okay. So for now, I think that I'm going to say like this is done. So you can do a couple more annotations on the image so that you can create so that like sorry. You can create, like when you draw more annotations, so then it will help when it comes to training the deep learning model. Okay, so ideally, I would actually try to train on all of the objects that are that have the same kind of appearance, or of the objects I'm looking for. And then after, once I'm finished with all of that, then I can go ahead and save this object into a mask. If you go to object settings, there's three options. You can do the export up to 8-bit binary, to 16-bit, or 32-bit. You should always export the meshes that you've drawn to match the bit depth of your input image. So in this case, my image is 8-bit. As you can see at the very bottom, if you look at the lower left corner, it says 3 nanometers per pixel, and then next to it, it says 8-bit. So then if I save this off as an 8-bit, then when I'm doing the training, it will Aivia will match it more. Aivia will match the bit depth, and so it won't cause any errors. But let's say you have a bit depth mismatch. Sometimes things can get dicey, so that's why I generally recommend just trying to match the bit depth of your source image. And I'm going to save this off. And this part is not really necessary, but I just want to show you guys what the output mask looks like. So I go to temporary files and go to the EMGT. So you can see this is the binary output that I have generated using the mesh contour editor. So now that I have my input image and my ground truth data, I can start training the deep learning model. Under the tools menu. So do you have any questions up to this point?
Nope.
Okay. Alrighty, so to train a deep learning model, I would go to Tools tab and then go to the Batch and Cloud processor. You'll open up this window, and you will need, in order for you to start training the model, you will need to add the folder that your data is located in. So to do that, just go on to click Add Local Folder, and then select the folder that your data is in. So in this case, I actually have the data in 2 separate folders. I have them in the temporary files folder and also the shared data folder. So I'm just going to add both of them in. So there's the temporary files folder, and then I'm going to add the shared data demo data folder as well. So to train a model, what you need is a raw input, which is your example image that you want to, the input image that you want to be transformed, and then the example, which is the ground truth or the annotated data. So for this one, I'm going to find the 3D EM analysis demo and assign. And when I select that, I can right click on it and say assign as raw input to set this as the raw input. And then going to the temporary files folder, I'm going to select my ground truth data and then say assign as example. And when you do the when you're training on a large number of data, sorry, go ahead. Oh, sorry.
I wasn't saying anything. I was just writing text, but I'll take an opportunity to say thank you for Alex and Matthias to join. I'm going to drop off. You're in great hands. Yeah, if anything else comes up in terms of questions that you want to ask me directly, you're very welcome. I'll leave my email there. Alex already has it, but I'll leave my email here in case you want to ask me anything else. Thank you, and yeah, have a good rest of the workshop.
Okay, thank you.
All right.
Thank you.
Thanks, Luciano. Okay, so continuing on. When you're training on the data, when you're doing the training, especially when you have a large number of 2D slices or maybe like 3D data sets, you want to make sure that the raw input and the example matches. So let's say if I have 200 slices of the image and I have 200 slices of ground truth, I want to make sure that the number that are the input slice matches the ground truth slice based on this number on the upper left corner. So, and if they're mismatched, then it will just generate really garbage results. So, and then for the training location, you can select any location you want. So it's also a good idea to just kind of copy that just for your own reference when the training is done. For the application, you can select either the 2D image segmentation or the 3D image segmentation. Generally, I think the 3D segmentation will give you better results for a 3D data set just because it takes into account of the information from the neighboring slices. And so there's a couple, and then there's also a couple of options that you can do. So there's also this idea of that you can train from scratch, which is that you're just using the network, but giving it completely new data for it to generate the result, for it to generate a new model. Or you can use transfer learning if you just click on this check mark here to kind of take an existing model and try to refine it with additional data. So if you have already trained your own deep learning model, it's a good idea that you just wanted to augment the model with additional information. It's good to just use the transfer learning option because it is a lot faster compared to the compared to training from scratch. And then when I select the transfer learning, there is also a new dropdown called model. You can actually select the model that you want to use for the transfer learning as kind of the base. So your segmentation is just fine. And then if you have your own model, then you just need to make sure that you also have that model in your local folder as well. Now, to train a model, I actually need 2 input data sets and two raw input and 2 example data sets. So you'll notice that like right now I cannot click on the create button to train a model because I only have 1 data set for each. So I don't know if I can actually assign this again. Let's see. Nope. Okay. So I'm going to cheat a little bit, and I'm going to close this for now. I'm going to save this image again, just to kind of show you. Like, of course, like if you have your own data set, it wouldn't have that problem. Okay. So now I'm going back to the batch and cloud processor. You can click, and when you click refresh, it will also update the folder information. So you should actually see additional files. I don't know if this is why this is not working. Okay. Okay, there we go. Okay, so I'm going to add these 2 to my data set. So now after I added the second data set, you'll notice that the create button is now working. So when I click create, so this will then it will move on to this new tab called process queue. And so like right now what it's doing is like it's making sure that the data is correct, and it's also going to grab the model and then it'll start the training. Let's give it a few moments. So sometimes like if you notice, okay, yeah, that's okay, good. So sometimes like you might notice that during the initialization process might be stuck. If that's the case, you can go to you can try to open up the log, and so you go to file options and then I think logging. You open up the log file, this will give you the information at the very bottom to tell you that if there's certain errors that you're running into. So hopefully that's not going to this is not going to happen in this case, but just kind of for your information, I think Trevor previously have demonstrated last week on how to figure out on identifying issues from the log on the Python side, but it will be the same thing because the log will also have information about Aivia Cloud. So this is training, so you can see there's a chart to see what the loss and what the accuracy percentages are, and then it'll run through this 200 epoch to try to generate the best result that matches what the ground truth looks like. So this will take like some time to do. So do you guys have any questions for me at this point? I think this pretty much wraps up the deep learning portion of the train that I want to show you guys.
So I just have a quick question. Do you need to have, so all your images must be the exact same dimensions, right?
Yes, absolutely.
Okay.
So sorry, I take that back. So each image pair needs to have the same dimension, but each image does not have to. So let's say if your raw data, you can have one raw data that is maybe like 512 by 512, and then another one that is 1024 by 1024. But as long as the ground truth for those matches the raw input, you're okay.
Okay. Okay, I get it.
Yeah. Yeah, and I think we actually have mentioned this in our wiki as well. So there are a few additional things that that would be good to know when it comes to doing the for the Aivia Cloud training. So actually, kind of forgot, you could actually also just type in the search now. I'm just so used to like just going to the Aivia wiki to find these information. So let's see. So I'm going to. Also, it has been a while since I actually read my own writing. So
and not just the dimensions of the image or the bit depth, but if you're working with something like restoration, you should try to have as best a pixel-to-pixel registration as possible. So in other words, if you have like a ground truth image, a high signal to noise versus a low signal to noise, when you're creating your initial model, those two should match up pretty much as much as possible.
Yeah.
Okay, that's good to know, because the STED give us very different signal to noise ratio from the Confocal.
Right.
So we'll be careful about this.
Yeah. Yeah. So if you go to the Aivia Cloud DL page at the very bottom, called Data Best Practices, you'll actually see. So we'll actually give you the information about what kind of image format we support and what's the image size and dimensions. So as I mentioned, the dimension and the bit depth needs to match. For training 3D models, you definitely need to have, it needs to be at least 256 by 256 by 16. So for example, so Alex, for the example of like with the confocal to STED, I know that like you will need to make sure that both the confocal and the STED have at least 16 slices. Even if you are capturing blank frames, you still need to make sure that they both match the 16 slices minimum.
Oh, okay.
Yeah, and then it only works on a single channel. And then for 3D, if you have a time lapse, it's good to actually separate them out into individual time points for training as well.
Okay, I would definitely need to revisit this.
Yeah, no problem. Yeah, like if you have any, so if you have any questions or if it's not working for you, just shoot me or Luciano an email, and then I can help you troubleshoot this.
Okay. So restoration is something I want to do between STED and Confocal, but right now the data set I have are not big enough. I do want to acquire more in order to make it worth playing with it and spending time with it. But yeah, I would definitely get in touch with you guys through Trevor in maybe a month or so.
Yeah, sounds good. Yeah, in my experience, the restoration is a lot more forgiving compared to the segmentation model. So instead of like, so you don't really, so in the segmentation, a lot of times you'll need, like maybe like 10 or 20 like fully annotated images for the restoration. Like usually, like if you can get that 10 pair of data, it's pretty, like you should get a pretty good result.
Okay.
So
okay, that's good to know. That's good to know.
Yeah.
But the 16 slides image is definitely something that I did not realize before.
Yeah. So for training the 3D, you will need the 16 slices. But if you just want to try it with the 2D, like with the 2D model, the 16 having less than 16 slices will also work as well.
So it's doing a projection.
I wouldn't do the
slice by slice.
Working slice by slice, so you can like pick and because I'm assuming that like your slice are all in focus, correct?
Yes. It's a very tight 3D stack right around the cell. So everything contains images. There is no out of focus information.
I see.
And I think it's about 8 slices thick, if I remember well. We usually take 8 to 10 because the STED is rather destructive way to image. So we can't really image like gigantic volume in the STED.
I see. Yeah. So for that, like the 2D should work because it only takes in the 2D information anyways. So that was so it will just treat all 8 of those slices as kind of like individual data points. So it actually like might even like be faster than to like need to acquire. You don't need to acquire like 10 images. You just need to acquire like 5 and it will have the same output. But of course then it won't be as good as the 3D. At least that would be my guess. But we haven't really played around a lot with like comparing like how it would look if we're just doing training in 3D versus just training in a 2D only model. So
I'm playing with microtubules. So since they're really like 2D structure pretty much, they're like 1D structure, like stretch over a single dimension. Maybe there won't be a big difference between 2D versus 3D.
Yeah, I don't think there will be much difference for sure.
But maybe some other objects.
Yeah, I think the only like kind of like the one thing that to be wary of is especially like for the ground truth is that if you're planning to do deconvolution, make sure that the deconvolution doesn't get too aggressive when it comes to suppressing the information around the edge of the microtubule.
Yeah. No, I don't deconvolve the STED. Well, not for this specific purpose.
Yeah. Okay. Yeah. So I think that. Yeah. So do you guys have anything else I can show you guys? I know Alex, you have like about 3 minutes before you have to hop off. So and Matthias, do you have any questions? Yeah.
I'm okay. I follow your instruction.
Yeah, just feel free to reach out to us if you guys have any questions afterwards.
Yeah. For sure.
Yeah. This is one area where I played around with quite a bit. So this is this is my very first demo, I think, in public. So hopefully it was.
You did a very good job.
Okay. Yeah, it's so great.
Yeah, this part's actually very easy because it's not very subjective at all. You're just plugging in models and file folders and things like that. So, but the results could be quite dramatic.
Yep. Yeah. So when the model is done, you can go to we can go to this folder. Sneaky wait, I can like open this up somehow. Anyway, so if I go, let's say for example, I go to this folder. So I haven't finished one at epoch yet. Yeah, so essentially, like if you're in this folder, you can actually we will actually save all of the epoch info, the model from at the end of each epoch. And if you already find something that is pretty good, you can just stop the training and then just take it. Just take the model.
It will not destroy the ongoing model.
Yeah, it will not. So it will. So each epoch will kind of represent, like, will be its own model, and then like there are like generally the idea for the deep learning is that you want to try to converge the model to some sort of like a high accuracy or like a low loss rate. And so like once it get to that point, like you can spend like another like couple hours to run additional epochs, and it might not change all that much. So so like if that's the case, you can always just end it a little bit earlier, so you can actually just take the model and just run with it.
I see. You're running it right now on your own GPU. Right?
This one is actually running on the GPU on Aivia Cloud. It's something
no,
that.
Sorry. Yes. Yeah. Right. You're on your. You're on the cloud. Okay. Yeah.
Yeah. This is So this is local training on the cloud, but there's also the cloud version of the cloud training. Yes.
Right, and this can be done locally on a computer as well. It's just a lot slower.
Yes, if you don't have the right GPU, yeah, I can see that.
And even if you do, even if you have a great GPU, it's generally faster, anywhere from I think 4 to 10 times faster in the cloud.
Okay, so it's using a different resource than the Aivia Web instance.
That's correct.
Okay.
I believe, right, Hoyen?
Yes, that's right. Yeah, so the GPU, I think for Aivia Web it's good, but it's not as good as the one that we can use with the cloud version of it, because with this set we only have one GPU. We only have one GPU, so the performance is just kind of similar to what you'd expect on a desktop. But for the cloud version of it, so for Aivia Cloud, it is actually using, I believe, 8 Tesla V100, so it will be a lot faster.
Yes, I can. Okay.
Yeah.
Okay. That's good. I have to switch to a different Zoom meeting. I'm really sorry for doing this. Do you mind if you have a snapshot of the ground truth at the end? Can you post it somewhere?
Yeah, sure. I can save that and just send it off. Yeah.
That would be awesome. That would be awesome.
Yeah. Okay. So this is actually this is the new run right there that you just saw, like that quick drop off there. So if you look at so now I can actually like open this one. So now if I open up this one. So now if I actually open up the file, you will actually see the folder. Sorry, you will actually see the model. Yep. There we go.
Okay.
Okay.
Yeah. That's so that.
Yep. So that's say two. Merci beaucoup for everybody for joining us.
You're welcome.
So I'm going to stop my sharing right now. Thank you very much. Again, if you guys have any questions, just let us know.